It is my privilege to introduce Professor Zoltan Bozoki. Dr. Zoltan Bozoki is a distinguished physicist and a head of the Department of Optics and Quantum Electronics at the University of Szeged in Hungary. He has a strong academic background, earning his MSc, PhD, and DSc degrees in physics in 1989, 1997, and 2012, respectively. Dr. Bozoki has made significant contribution to the field of photoacoustics with notable achievement in the development and successful commercialization of photoacoustic instruments for diverse applications, including the oil and gas industries and environmental monitoring. His innovative work has not only advanced the understanding of this field, but also has provided practical solutions for the real-world challenges. In recognition of his outstanding contribution, Professor Bozoki has received various awards and honors, with Gabor Dennis Award in 2017 being a notable testament to his excellence in the field of photoacoustics. His work continues to have a substantial impact on both academic and industrial aspects of optics and quantum electronics. On behalf of the RIOS members, I welcome you, Professor, to this webinar, and I also welcome all the invited guests and participants to the webinar. Now, I kindly request Professor Zoltan Bozoki to begin the presentation. Over to you, Professor.
So I share my presentation, and the title is the Basics of Photoacoustics for Gas and Aerosol Concentration Measurement. And as an introduction, I like to categorize photoacoustic in three different categories. First, we can talk about qualitative photoacoustics. Qualitative photoacoustics has two subcategories. We will measure photoacoustic spectra, and we would like to understand the origin of the photoacoustic spectra, and we would like to interpret the photoacoustic spectra. This is the first approach, and I think that photoacoustic is also an excellent tool to understand the working or principles of system theory. So step by step, how the photoacoustic signal is going through the system, and how starting from the excitation until the detection and beyond the concentration measurement. So all this process is a nice example of system theory description. This is qualitative photoacoustic. Then the next step is semi-quantitative photoacoustics, which means that we have some basic equation of photoacoustics, and these basic equations really capable to estimate the strength of the photoacoustic signal. If we know all the parameters of the measurement, we will have a good approximation of the measured signal. And we can also, if we have a properly calibrated photoacoustic system, and the system also includes various self-checking and self-correcting algorithms, then we can really, from the photoacoustic signal, we can calculate the measured analyte concentration. So it works like analytical instrument, really. And the quantitative photoacoustics, which I call quantitative photoacoustics, is when without any calibration, strictly based on the basic equation of photoacoustics, one could be able to from the measured photoacoustic signal directly calculate the concentration. And this is very important. If we could achieve a calibration-free photoacoustic system, that would be a huge step ahead, because as you know, that all the system is only as accurate as the calibration, as the accuracy of the calibration. So even if one has a perfect system, an excellent system with all the self-checking and self-correcting algorithms implemented, but the calibration is inaccurate, then even with the best system, the concentration measurement will be inaccurate. So calibration is a very critical issue, and the best system, which is absolute, meaning that there is no need for calibration. Then one very serious factor of inaccuracy is eliminated. Okay, so I just explained the three categories of photoacoustic. I hope, should I repeat something, or can I go?
No, it's okay. It's good. We understood.
Okay, let's go further. Okay, let's first talk about the mechanism of photoacoustic signal generation. So first of all, we have a modulated light. It can be periodically modulated, or it can be a pulsed series of laser pulses. If it's periodically modulated, like switch on and switch off, either amplitude modulation or wavelength modulation, then during the on stage, the molecules, the targeted molecules absorb the light and going into an excited state. And after that, there is the excitation of the molecules, so they go back to the ground state. So periodic excitation means periodic pumping of the energy into the system and then going back into the ground state. Then, especially in the mid-infrared or near-infrared, and also in the when the pressure is close to atmospheric pressure, most of the molecules get rid of this excess energy pumped by the laser via non-radiative relaxation. So simply these excited molecules has a collision with other molecules, and the energy which is originally in some low vibrational excited states, via collision goes to translation. Energy translate into the translational degree of freedom, which means that the illuminated molecules and the neighborhood of these illuminated molecules gets an increased kinetic energy. And of course, kinetic energy means temperature variation, and the temperature variation causes density variation and then pressure variation, and the pressure variation then generates an acoustic signal, sound, generates a sound. So the laser wavelength is tuned to an absorption line of the targeted molecules. Modulation means that the absorbed light power varies in time. Then molecules are periodically excited to a state with higher energy, and then excited state relaxes to ground state. Excess energy is converted to heat via molecular collision, and temperature increase generates density and pressure increase, and then pressure variation propagates as a sound, finally generating a standing wave in the closed volume of the photoacoustic cell. So you can see here some basic properties of the photoacoustic signal. First of all, the frequency of if it's a periodic modulation, we are talking about periodic modulation, then the frequency of the sound will be equal to the modulation frequency. This is very important. And second, the signal, the acoustic pressure wave, the amplitude of the acoustic pressure wave is bigger if there is more light power pumped into the system, and if there is more light absorbing molecules. So the signal, the photoacoustic signal is directly proportional to the concentration of the analyte. And if there is no absorption, because there is no light absorbing molecules in the system, then the photoacoustic signal will be zero. That means that this is really a zero background measurement method. So already some very clear advantages we can see in this figure. But let's now turn to the components, the main components of the photoacoustic system. Let's talk about first the laser. So the laser is tuned to an absorption line of the targeted molecules. So it must be a wavelength tunable laser, and it is modulated at the acoustic frequency corresponding to the resonance frequency of the photoacoustic cell. So if the photoacoustic cell has acoustic resonance at 4 kilohertz, then the laser modulation must be tuned to 4 kilohertz, to the resonance frequency of the photoacoustic cell. As far as the detection cell, which is of course supplemented with the gas handling system, is concerned, uh, of course, normally, at least normally, we should put optical windows at the entrance window and the exit window for the photoacoustic cell, so the laser can go through the cell. Although there are windowless photoacoustic cells, and I'm not speaking here about them, but the optical window must be fully transparent at the laser wavelength, not to cause some interference effect, some resonate Fabry-Perot resonator effect. And a properly designed photoacoustic cell can operate it in a continuous gas flow mode. So there is no stopping. It's not a good practice to stop the gas flow during the measurement, because absorption and desorption of the targeted molecules will have a big disturbing effect on the measurement. It's bad. It's best if there is a continuous gas flow through the photoacoustic cell. And if the photoacoustic cell is properly designed, then there is a amplification of the acoustic signal. So we can generate a standing wave, and the standing wave will amplify the signal, the original signal, whenever there is a coincidence between the frequency of laser modulation and the acoustic resonance of the photoacoustic cell. So as I said before, if the resonance frequency of the cell is 4 kilohertz, then the modulation must be at 4 kilohertz. This is very simple. And electronics of the photoacoustic system is also very important because it controls the laser wavelength and also controls the modulation parameters of the laser. And for diode lasers and quantum cascade lasers, This wavelength tuning and modulation is done by adjusting the laser temperature and the laser current, the unmodulated part, the non-modulated part of the laser current, and also the modulated part of the laser current. The other goal or other purpose of the electronics to detect the photoacoustic signal and to quantify the photoacoustic signal. So at the end, we must say that how many millivolt of photoacoustic signal is generated by on the microphone. And for this, we must use lock-in technique or synchronous sampling technique. So we must use a phase-sensitive technique because usually the microphone signal is weak. So, for example, if you put it on an oscilloscope, then you won't see, normally you won't see the generated photoacoustic signal because the broadband noise of the microphone is much bigger than the useful part of the laser absorption generated part of the microphone signal. Only after lock-in detection technique, filtering out the noise by the lock-in detection technique, one will be able to see the useful photoacoustic signal. So lock-in detection technique is absolutely necessary for a photoacoustic measurement. And if the electronics is good, properly designed and built electronics, then it also executes various self-checking and self-correcting algorithms. For example, the laser wavelength must be on the top of the absorption line. This is very important. And if the laser wavelength is shifting, then it must be shifted back to the top of the absorption line. And also the laser modulation frequency must be equal to the resonance frequency of the photoacoustic cell. So if the composition of the gas within the cell is changing, and due to this change, the resonance frequency is changing of the cell, then the laser modulation must follow this changing resonance frequency. So in this sense, the laser wavelength control and the resonance frequency control is somehow the opposite story, because for laser wavelength we tune back the laser, but the wavelength of the laser to the absorption line. So we change the wavelength of the laser, but for the resonance frequency, we are changing the resonance frequency. We cannot tune back the resonance, acoustic resonance frequency. Of course, we cannot tune back to the original modulation frequency. And also very important for the electronics, that from the photoacoustic signal, so from the lock-in amplified and lock-in generated microphone signal, the electronics calculates the concentration of the targeted analyte with the help of pre-programmed calibration constants. So previously we calibrated the photoacoustic system, and so once we are measuring the photoacoustic signal, from that, with the help of this calibration constant, we can calculate back the concentration of the measured analyte. Okay, and normally I have a question answer mode here. So I usually asking the audience to answer my question, but this is quite impossible for a remote presentation. So I will let some time for you to try to answer the questions. But basically, I will answer my own questions. So the most important parameters of the laser in a photoacoustic measurement is the light power, the wavelength of the laser, because it must coincide with the strong absorption line of the targeted analyte, the tuning range of the laser, so how many nanometers or centimeter minus one we can tune the laser, because it is important to tune exactly on the top of the absorption line. And also it's important that the emission line width of the laser, how wide is the emission of the laser, because if it's too broad, emission is too broad, then only part of the light energy will coincide with the targeted absorption line, and so the signal will decrease. So the best is if the line width of the emission is narrower than the width of the targeted absorption line. It's also very important that how stable is the wavelength of the laser. This is also a critical question, but our experience shows that no laser has, let's say, at least diode lasers or quantum cascade lasers. They do not have sufficient wavelength stability. It is called aging effect. So the laser wavelength is drifting in time. So we must apply here a correction algorithm to tune back the laser to the absorption line. And also it's a critical question that how the modulation, what is the effect of the modulation on the laser wavelength, the line width, and so on. So it's the effect of modulation must be very well understood and very well measured. So these are the most important parameters. What are the most important parts of a detection cell? The microphone, of course, the windows of the cell, and there is usually a central resonator which really generates the photoacoustic signal. And besides the central resonator, there are some buffer volumes in the system. And for the electronics, as I explained before, we have a laser driver, we have a microphone amplifier, we have a signal processing unit, which is usually a lock-in detector. And also, of course, we have a gas handling system. So if we measure in the environment, or if we measure in a process stream, then it is very important to ensure that the gas from the measured system goes into the photoacoustic cell. So we have a gas handling system, and this and similarly to the calibration, as I explained, if the gas handling system is not good, then it will spoil the measurement, because even if the photoacoustic cell is excellent, the gas handling system can be bad, meaning that the concentration of the gas going through the gas handling system is changing. And of course, in this case, the concentration measured in the photoacoustic cell will not be the same by the concentration at the beginning, at the measured concentration. So the gas handling system is very critical. So there is a sampling inlet. The sampling inlet is very critical that if it's badly designed, then the sampling inlet will make some false sampling, spoiling the measurement. And also there is a flow control unit. The photoacoustic signal is so normally the gas flow through the photoacoustic cell is something like 200 cubic centimeter per minute. So, but if it's 150 or 200 or 50, it doesn't matter. But there is a range of so it does not, it's not necessary to have a very accurately set volumetric flow rate. The flow rate can vary. That's not a problem, but it's not good if there is a range of the optimum volumetric flow rate, and it's not good if the flow is below this rate or above this rate. So for that, there is a need of flow controller unit. And of course, one must bear in mind the Bernoulli law. So if for example, on a very thin tube, one tries to push through high volumetric flow rate, then there will be, due to the Bernoulli law, there will be a big pressure drop in the system, which practically hinders the possibility of a good measurement. So some general system design principles must be one must take care of this and obey these principles of system design. Okay, so now this is the background and some examples of successful application of the photoacoustic system we developed here. We made hydrogen sulfate, water vapor, and carbon dioxide detection photoacoustic system for the oil and gas industry. And we, a spin-out company of the university, implemented at various places worldwide these instruments. And the critical part of this system is not actually not the laser and the cell and the electronics. It's very important. So I'm not saying that it's not important, but the self-checking and self-correcting algorithms are the most critical part of this parts of this system, because otherwise it can happen that photoacoustic system which operates perfectly under laboratory environment is making absolutely nonsense measurements under field conditions. So moving from the laboratory to the field is a huge step, and it's pretty sure that after the initial measurements and based on the results of the initial measurements, the system, we must bring back the system into the laboratory and make further improvement of the system. So this is the lesson we have learned from our experience. We have also a nice system which operates at the passenger aircraft and measures water vapor and total water concentration in atmospheric air. So water vapor is the gaseous part of H2O molecules. Total water means that gaseous water vapor plus ice crystals and cloud droplets, so in liquid and solid form of water vapor. And our photoacoustic instrument is capable to do this measurement, and it is a very important measurement because atmospheric chemistry is very different in clean air and in clouds. So our photoacoustic system is working like a cloud detector. So whenever the total water concentration is higher than the water vapor concentration, then we know that the aircraft is flying in a cloud. And then in a cloud, the atmospheric chemistry is completely different than in open air. We also working on a lot of medical applications. Photoacoustic is very good for medical application, like the measurement of methane in exhaled air, a very important application. Also, we are working on ammonia emission and recently the nitrogen oxide emission from soil, and also by various agriculture activities. We have a PhD student from India here, and he already made some successful applications of the photoacoustic instruments in agriculture applications. Okay, so these are these are just few examples. Why it is worth dealing with photoacoustics, and let's see now some unique advantages of the photoacoustic method. So first of all, there is a very nice linear proportionality between the concentration of the measured analyte and the photoacoustic signal. And this is valid, this proportionality, this linear proportionality is valid over 5 or 6 orders of magnitude in concentration. So, for example, from ppb up to several percent, so a huge range. And also very important that concentration measurement by photoacoustic is executed directly in the gaseous phase. So there is no phase transition. We do not have to condensate the gas, or we do not have to absorb or adsorb the gas. The light goes through the gas, and there is a direct measurement of in the gaseous phase. And if we have a proper light source, I would say that at least 5 milliwatt light power and tunability to a strong absorption line. Then with the photoacoustic, depending whether we are doing near infrared photoacoustics or mid infrared photoacoustics, ppm, ppb, or even sub-ppb concentrations are measurable. Of course, ppm means that from 1 million of molecules, one is the targeted analyte, so 1 per million. ppb means that 1 per billion, and even smaller concentrations can be measured by photoacoustics. It's also very important that the volume of a photoacoustic cell is small, only a few cubic centimeters, which makes possible to measure with fast response time. So if there is let's say 200 cubic centimeter per minute flow rate, and the photoacoustic cell is only a few cubic centimeters, then it's possible that the response time of the system, so the time needed to follow the sudden concentration variations is less than a second. So it's a very fast system. And photoacoustic is a very simple setup. It has a very robust construction. It has long-term reliability and fully automatic operation. And then if you ask what is the number of measurable components, and my question would be that what determines the number of measurable components with one photoacoustic system with one laser, then the answer is of course the tuning range of the laser, how wide is the tuning range of the laser, and how many molecules have at least have a sufficiently strong absorption line in this tuning range. Some lasers like gas lasers, carbon monoxide or carbon dioxide lasers have a remarkably wide tuning range, and other lasers like diode lasers or quantum cascade lasers usually only one or maybe two or three components are measurable by this laser because in the tuning range of the laser only a few absorption lines are available, and in principle if you have five components within the tuning range, so five components have strong absorption line within the tuning range of the laser, then one can say that five components can be measured. The concentration of five different components are measurable with the photoacoustic system. In practice, this is not necessarily true. Why? Because it's possible that these absorption lines are too weak for accurate measurement, but it's also possible that these absorption lines overlap. So there is no guarantee that the absorption lines are sufficiently separated. And if the absorption lines overlap, that can spoil the accuracy of the concentration measurement, or in a worst case, it can make impossible to make the measurement. Okay, the laser we use, diode laser and quantum cascade laser, have narrow tuning range, and as a consequence, they can measure typically only one component. And okay, some cases there might be more components absorbing within this narrow tunable range, but in this case it can really happen that the strong absorption lines overlap, causing some problem. So it's very important to emphasize that photoacoustic is only usually capable to measure only one component. So it's not a multi-component analysis system, like for example, a Fourier transform infrared system or ion chromatography or whatsoever. It only, in the best case, it only measures one or two components. So, but this is for a certain applications, this is sufficient. So the photoacoustic method is very competitive, used in the natural gas industry, in medical diagnostic, environmental monitoring, and it's very interesting. Okay, what I want to say here that when we built the photoacoustic system and we had the first successful applications, and a lot of people has the same experience, then of course it is the best to measure in clean gas, like in nitrogen or in synthetic air or in real air, to measure one component. This is a very nice measurement and very good experience. But it turns out that photoacoustic is not really competitive in these simple applications. Why? Because it turns out that for simple applications, there are cheap and reliable sensors which can also be usable. And because you must see that photoacoustic is not really a cheap detection technique, because the laser has some price, of course, and then the cell must be fabricated, the gas handling must be built, but most expensive is the electronics of the photoacoustic system. Why? Because it includes a lock-in. The lock-in detection usually makes the photoacoustic that electronics expensive, but not only the lock-in, but also the cell temperature must be stabilized very accurately. The laser temperature must be stabilized very accurately. So the lock-in and all these stabilizing components makes the photoacoustics not very cheap. Uh, is my time over? Should I stop now?
No, Professor, you can carry on for like 5 or 10 more minutes.
5 more minutes. Okay. And it turned out that for complicated gas mixtures like natural gas or gas mixtures like exhaled air, which are very complicated gas mixtures, it turned out that photoacoustic is the best for these applications. Why? Because competitor alternative instruments cannot measure accurately in such complicated gas mixtures. And to be honest, at the beginning, our photoacoustic system was not able to measure accurately, but one by one, we introduced this self-checking, self-correcting algorithms, and so at the end, our system was not affected by variation in the gas chemical or physical properties, but our measurements were accurate even under these rough measurement conditions. So I would normally, to be honest, I would normally avoid measurements in complicated and varying gas mixtures by photoacoustics because this is really requires a careful system design and careful operation. But at the end, it turned out that we must go into this direction because for simple applications, competitive technique can outperform photoacoustics, but as soon as the application becomes a complex and a challenging task, then photoacoustic can really be the winner. So that was the most important lesson we learned from photoacoustics. Okay, so I skipped this part because I'm at the end of my presentation. Just very briefly, I show you the principal equation of photoacoustics, and basically this will be the last part of my presentation. So the microphone signal at the frequency of the laser modulation. So the amplitude of the microphone signal is proportional with the light power. So the higher the light power, it's the better. The microphone sensitivity, which has a unit of Pascal, millivolt per Pascal, meaning that 1 Pascal amplitude of acoustic signal, how many millivolt electric signal generates by the microphone. And there is a cell constant, which is the efficiency of acoustic signal generation in the unit of for 1 milliwatt light power and 1 centimeter minus 1 optical absorption coefficient, the acoustic signal. This is basically depends on the geometry of the photoacoustic cell. With a good geometry, with a properly designed cell, this could be a big number and making the photoacoustic system sensitive. And alpha null is the specific optical absorption coefficient of the measured component in centimeter minus 1 per ppm or ppb, whatever you want, which means that in case you are using a strong absorption line, then this alpha naught will be higher, and then the photoacoustic system will be more sensitive. And finally, you can see here the concentration of the measured analyte, and you can see the beauty of the photoacoustic method, because the photoacoustic signal is proportional with the concentration of the measured analyte. This beautiful linear relationship. And there is some background signal like light absorption on the walls or the windows of the photoacoustic cell, which should be minimized or completely should be eliminated. And my last thought is, of course, that I'm talking about signal, but in an instrument, in an analytical instrument, we are never interested in the signal alone, but the most important parameter is the signal to noise ratio. So if we optimize a system like this photoacoustic system, it's not sufficient to maximize the signal, but we must maximize the signal to noise ratio. This is the most important. So there are plenty of more I wanted to say, but I think basically I told you the most important part of the photoacoustic measurement. Here at the end of my presentation, there are some questions which one can answer for practicing that he or she really understood the photoacoustic signal generation. Okay, so thank you for your time for listening my presentation.